Okay, here is the derivation for the critical conditions and the van der Waals equation. So, a little bit of background. The van der Waals equation is P is equal to N RT over V minus NB minus A N squared over V squared. Or it's equal to RT over Vm, the molar volume, minus B minus A over the molar volume squared. So these two coefficients, A and B, are known as the van der Waals coefficients, where B is a reflection of the repulsions between non-perfect gas molecules, and A is indicative of the attractions between non-perfect gas molecules. To see how this kind of makes sense, let's look at the relationship between the van der Waals coefficients and pressure. So if we increase B, that means Vm will get smaller and this whole first term will get larger. So when you increase B, you increase pressure. This makes sense because if the repulsive forces are high, then these gas molecules will not want to be near one another. So this will increase the frequency of collision and the force of the collision with the container. So that makes sense. What about when you increase A? Well, if you increase A, you increase the magnitude of this term, which effectively decreases pressure. This makes sense when you think about the gas molecules and how, if they're attracted, they are going to impact the walls of the container at a lower frequency and at a lower force, which results in a lower pressure. So these relationships make sense. What about the critical conditions? What does that mean? Well, the critical temperature is the highest temperature in which the substance can exist as a liquid. So, above the critical temperature, any amount of compression, despite any amount of compression, the substance will never be able to liquefy. Right, so this means that at a temperature greater than the critical temperature, the substance is always in a gaseous form or otherwise in a supercritical form. Below the critical temperature, the substance acts normally, and as you compress the substance, it eventually becomes a liquid. So that's that. So given a graph of pressure versus volume, and using the van der Waals equation at a constant temperature, you'll get lines that look sort of like this. So here, you'll see that the first derivative is equal to 0, and that the slope is 0, if I can draw it right. And then the second derivative is also 0, because concave down, turns into concave up. So it's at this point that we can evaluate the critical conditions. So in order to evaluate the critical conditions, we come up with a system of equations using the first derivative and the second derivative of the van der Waals equation. So let's do that now. So van der Waals equation, P equals RT over Vm minus B minus A over Vm squared. I'm using molar volume because it's easier and it's just overall less variables. So the first derivative, dP with respect to dV, is equal to the following. Okay, that's the first derivative. and we can set this equal to 0. So the second derivative of the van der Waals equation with respect to the molar volume is equal to the following. Which we can also set to 0. So here we have two equations, the first derivative and the second derivative. And we can set them equal to each other because both of them are equal to 0. So what we traditionally want to do is we want to get rid of the most troublesome part of the equation when we add them together. And that would be this Vm minus b squared term. So I'm going to multiply the first derivative by 2 over Vm minus b in order to equal this term on the second derivative so we can cancel the terms out. So let me multiply the first derivative by 2 over Vm minus b now. Now we can add this second derivative, so this expression plus this expression. And we can set this equal to 0, because 0 plus 0 equals 0. So these terms cancel out, and we can move this negative term to the opposite side of the equals sign. Or there you go. Okay, I forgot there you go. So we can cancel out 3 of these 1 over Vm terms, and this leaves us with 1 there. We can also cancel out this a, and we can divide by 2. That gives us the following: 2 over Vm minus b is equal to 3 over Vm. Now we can cross multiply and cancel out. So negative Vm is equal to negative 3b, and Vm is equal to 3b. And since we evaluated the derivatives at 0, Vm is equal to Vmc, or the critical molar volume. Okay, so now that we have Vmc, what about Tc, or the critical temperature and the critical pressure? Well, in order to find the critical temperature, we can plug in our value for the critical molar volume of 3b into either the first or second derivatives here. I'll choose the first because it's simpler to evaluate than the second. So here's the first derivative of the van der Waals equation with respect to Vm. If we can plug in 3b for the Vm terms and evaluate for T, then we can find the critical temperature. This is equal to 0, obviously. Okay, so now we solve for an expression for T. So that's equal to negative 2a 27b cubed multiplied by negative 4b squared over r. So let me just combine those two terms. So that'd be a positive 8 ab squared over 27 b cubed r. So that simplifies to 8a over 27 b r. So that is our critical temperature. So the only thing left to derive is the critical pressure. So in order to do that, all we need to do is plug in Tc and Vmc for our original van der Waals equation. So let me just rewrite it. VRT over Vm minus B minus A over Vm squared. So it's equal to, this numerator is equal to, these r's will cancel out, 8a over 27b over Vmb, which is 2b minus a over 9b squared. So this becomes this. Okay. And from here we can multiply by the least common multiple in order to add or subtract the fractions. So this stays the same, and I multiply the right fraction by 6, so I can subtract the fractions. Is equal to 2a over 54b squared, and this obviously cancels out. A over 27b squared is equal to the critical pressure. So here are all the expressions for the critical conditions using the van der Waals equation.